All right, everybody. We'll get the evening part of this started. Welcome to the end of day one. I don't know about you guys, but I am totally toasted in the best of ways. I went to a bunch of talks. I drove the remote control car and failed miserably. I tried to ride the bike that could not be ridden, and I could not ride it. I don't know. I don't know how many people tried, but that was crazy. I would first like to say thank you for the lovely comments on Twitter this morning. It totally made my day. My ego is huge, so you're hired. You can do that again. That was great. And I would like to ask, did you try something new today? And I know the part that everybody always dreads. Please turn to your partner and tell them what you learned or what you did that was new today. I'll give you about 1 minute. Turn to somebody near you. What did you try? All right. So, whether it succeeded or failed, I think pat yourselves on the back for trying something new. It's always challenging. And before I get into some of the logistics and introduce the closing speaker tonight, which I'm really excited about, I want to there are people here that have organized this conference, of course, that have put together these talks for you, and there is a lot of work that goes in behind the scenes. So the first thing that I would like to do is, please, those of you who are the program makers, that have watched the videos, that have dealt with the speakers, please come up on stage because we would like to thank you. Yeah. So, you can now recognize the people here, so please, when you see them and you've seen a talk that was particularly good, you know who to thank. A lot of work goes into getting speakers for the conference. You don't get to just submit a talk and they say yes. You have to actually, they're going to watch your videos of previous talks. They're going to test everything out. And then, there's a lot of hoops you have to go through. So these are the people to thank when you see them in the halls. Thank you all so very much for this amazing conference. All right, so a couple of logistics. Tonight, there is a quiz night at Babel. You do have to sign up on the website, and I put here, if you go to øredev.org/info, you can sign up if you want to go to the quiz night. Just because it's a smaller place, we want to guarantee that people can get in. So if you've registered, you're guaranteed to get in. Also, there are free train tickets and a free drink ticket at the information booth, so be sure to pick that up. It's really important. The other logistic is keep your badge, because you're going to need it tomorrow and Friday when you come back. So please remember to keep your badge. And we're going to do an experiment. It's time for some feedback. Now, this is a new form of experiment. It's going to take about 5 minutes, but I'd like you to all please get out your phones. And I'm going to go to Menti again, and we're going to go through the sessions, not one by one, but by hour, and you're going to say which sessions you attended, and whether it was a thumbs up, thumb down, and we can see the results in real time. So it won't be for each individual speaker, it will be for the time slot. But we'll see how this goes. So remember, it's an experiment. So for the 10 to 10:40 slot, which talk did you attend, or did you take a break? Oops, and internet connection would be good. 1 second. That's my problem here. Here we go. There we go. And really, this is your one and only opportunity to offer feedback unless you want to send separate emails to the organizers with specific feedback. So I'm going to go through this relatively fast. Okay, and for your session, here's some numbers coming in still, last minute. For your session, would you give it a thumbs up or a thumbs down? You're going to have to go to move to the next slide. You'll get a little notification on your phone. All right, so far so good. Not bad. First sessions. All right. Now, speakers will get their individual feedback. For the purpose of this, everybody, we're getting the collective feedback. So for the next session, from 11 to 11:40, which talk did you attend? Pretty nice even distribution. That's great. Okay. Quick, push the button quick. Here we go. And what did you think about the second session? Different. Good to know. This also helps the program makers decide what to bring for next year, what style of talks. All right, here we go. Third session, from 1 to 1:40. What did you attend? All right, and what'd you think? Okay, we're almost done here. Keep your phones out. You don't see that very often. All right, the talk that you attended from 2 to 2:40. People are taking a break. Yeah, my brain is full after today, man. All right. Oh, fast voting. This is great. And what did you think? This is great. Last year, what happened with the voting things, we got about 20 people voting for feedback. So now we get feedback from 400 plus people, so that's really good. And the last one, or I think second to the last. Okay. What'd you think? Uh-oh. It's the afternoon dip. Had nothing to do with the speakers. All right. And last one, I'm sure. Okay, a couple more seconds. Here we go. What'd you think? Like, whoa, no way! Okay. All right. Thank you all for voting and for giving the feedback. It's really important for the conference organizers to receive this. So this was an experiment this year. You can let us know what you thought about it and if you think there's a better way. So, let me get my mouse on the right screen. Those over there. Okay, before we get to the closing keynote, please stand up and just stretch your legs a bit, right? Because we have another 50 minutes. Just whatever, watch out for your neighbors or don't. Yeah. Some jumping jacks, put it around. Get some blood flowing because you're going to want to listen to this one. All right. Thanks. So our closing speaker for today is Adam Tornhill, and I'm very excited to introduce him. And like many of you, he got his first passion for software with the Commodore 64 and programming it, and he started to wonder, well, how do you program this thing? So that's where it all started. Now, he's since then written 4 books. And as someone who's written a book and has said, never again, I'm really in admiration of writing 4 books. And his most recent book is called Your Code as a Crime Scene, which is what we'll be talking about today. So he currently uses his superpowers in both software development and psychology to show how teamwork and software architecture are connected. So perfectly in line with the theme. And some things that you might not know about Adam is he was a Taekwondo trainer, and he played in a black metal band. And he's a big fan of modern history. So it gives me great pleasure. Please welcome to the stage Adam Tornhill.
Good evening, everyone, and welcome to this therapy session. So, psychotherapy is all about building awareness and understanding, which we can use to form healthier habits. And in this session, I want us to do the same thing for software development. And we're going to do it through the lens of psychology. So let me share my journey to psychology. It all started back in August of 1997. At that time, I joined my first real job as a professional software developer. However, I had been writing code for a long time prior to that. I've been writing code for almost 10 years, so I thought this is going to be pretty straightforward. However, I pretty soon noticed already on my first day that large-scale corporate development is an entirely different beast. First of all, I noticed that no one really had time to show me what to do. No one really had time to onboard me. And the reason for everyone's busyness was because all my colleagues were busy in wrapping up a major software project. So this was a project that's been going on for 3 years. And it involved both new hardware, custom hardware, as well as a number of new subsystems. Fortunately, It was now approaching its completion date, and there was only a single thing left to do. The only thing left to do was to integrate it. And as you can imagine, that didn't went as straightforward as the plan saw. So, in fact, 6 months later, that project had to be cancelled and restarted with a different scope. So that was my introduction to large-scale software development. And I have to admit, from there, it pretty much just went downhill. So at some point, I really had to take a step back and start to ask myself, why do all these incredibly friendly, talented, and smart people that I work with, why do so smart people make so stupid decisions? And I couldn't really find the answer to that within the software industry, so I decided to look elsewhere. I decided to pick up psychology. And initially, I just wanted to do an introductory course. But let me tell you, psychology is really, really fun. So I actually ended up spending 6 years at the university. It was nothing I planned for. I got my degree in psychology more or less by mistake. But at the same time, I was working as a software developer, and that gave me plenty of opportunities to relate the two fields to each other. And the first thing I wanted to figure out is, why is it so hard to succeed with software? Why is it so hard to write good code? And I have to admit that the more I learned about cognitive psychology, the more surprised I got that we are capable of writing any code at all. It shouldn't be possible. Software should be too hard for us. And yet, we do it every single day. And sometimes our code even works. So I think a better question is that instead of asking why programming is hard, let's ask why it's possible at all. Because that's where I think we can get some insights. Now, what about therapy? Do we, as an IT industry, do we really need therapy? That is, do we need to improve? Over the past 4 years, I've been fortunate to work with code analysis, both on the tooling side, but also in working closely with different organizations. So that means I spent a significant amount of the past 4 years looking at other people's code. I spent a lot of time working with organizations and seeing how they approach different situations and challenges. And I've seen some patterns that I would like to share with you today. And as a starting point, I want us to consider this. Remember the project I told you about, right? My first large-scale project. That was a classic waterfall project, right? And today, we might laugh about it. But I do think we should ask ourselves, why did so many companies adopt waterfall back in the day? Because they did. And even more important, we should ask ourselves, what are we doing today that the next generation of developers are going to laugh at? What's the waterfall of today? I do have some answers for that, and you will see them sprinkled throughout the presentation. So we're going to visit both technical and social challenges of software. And let's start with the team side of software. Let's start by talking about brainstorming. So how many of you have taken part in a brainstorming session? Wow, that's pretty much everyone, right? What I find so fascinating about brainstorming is that it's a pretty old concept. It was written down in the 1950s. And the original promise of brainstorming is a promise of productivity. Working in a team, in a brainstorming session, we can generate twice as many ideas as we can do on our own. Now, you might think that if we have this creative thinking process that's 60 years old, is used all over the place, then maybe, just maybe, there might be a few studies on it. And guess what? You would be right. There are a ton of studies on brainstorming, and what they all show pretty consistently is that it doesn't work. In a traditional brainstorming session, not only do we generate less ideas, the quality of those ideas suffers as well. So we lose some kind of productivity, and that loss is what psychologists refer to as process loss. Now, process loss is a concept from social psychology, and social psychologists in turn have borrowed it from the field of mechanics. And the idea is that just like a machine cannot operate at 100% efficiency all the time due to things like friction and heat loss, neither can a team. And the kind of process loss we get depends on the task that we do. But within a field like programming, where not only are our tasks complicated, they're also interdependent. Most of that process loss tends to be due to things like coordination and communication overhead. And when social psychologists study coordination overhead, they use some very creative techniques. Because what they want to do is they want to find a task that's sufficiently complicated to involve coordination, yet at the same time is easy enough to measure. And a perfect fit for that is this, a tug of war. So if you take part in a psychology experiment like this, what's going to happen is that you're going to be teamed up in a small team, and you're going to have to pull on a rope. And the psychologists are going to measure how much force does each individual generate. And then they do a variation on the experiment where they add more team members, 4 people, 5 people, and so on. And what turns out is that the potential productivity, pretty much as predicted, it increases linearly, right? So the more people we add, the higher the potential productivity. What I find so fascinating is that the real productivity is much lower. And it's much lower because the coordination costs, they increase faster than the potential productivity. Now, the reason I tell you this is because we have our fair share of heat loss and friction in software too. We just know it under a different name. We know it as the mythical man-month. And as we saw in the morning keynote, the mythical man-month is famous for Brooks' Law. And Brooks' Law says that adding manpower to a late software project makes it later. However, Brooks' Law is 45 years old. And based on my experience, I would like to revisit it. And I would actually claim that adding more people to most software projects makes them later. And the reason for that is due to process loss. And you have the graph that explains it here. So on the y-axis, we have the time to completion, right? Measured in months. And the x-axis is the number of people we can add to that project. And as you see, we can add people to it, and we get a shorter completion date. We get the task done quicker. However, there is this turning point, and beyond that point, each individual that we add is going to contribute to a delayed completion date. The reason that happens is because the potential productivity increases linearly. With each individual that we add, we get a fixed number of hours extra available, typically 40 hours here in Sweden, right? However, the coordination needs increase much more rapidly. So beyond that turning point, the additional coordination needs are going to consume all those extra available hours and then some. Now I would like to ask you, has anyone ever experienced this on a software project? Wow, depressingly many hands. Wow. Yeah, I've seen it a number of times myself, and I actually think that it's much, much more common than what we think. Most of the time, an organization doesn't know when they fall into that trap. And I think there's a very good reason why we keep repeat these mistakes. And I would like to show you by doing a small test. So please, have a look at the following piece of source code. This is a small part of a larger program. Based on that code, who can tell me if this code is written by a single individual that keeps all of that information in their head so that we have a key personnel risk, or if this code is written by 5 different feature teams and is a constant coordination bottleneck? That's right, we cannot tell. And the reason we cannot tell is something I like to call the great tragedy of software design. That the organization, we people who build a system, we are invisible in the code itself. And as a consequence, we tend to treat symptoms instead of the real issues. So just to give you some examples, a couple of years ago, I worked at a company that experienced pretty severe merge conflicts. So they were spending a lot of time merging different feature branches. They decided to resolve that by buying better merge tools. So we're basically throwing technical solutions at people problem. Or maybe you experience long lead times, so let's add more people to the project so we can get things done quicker. I would like to claim that if you experience any of those symptoms, you're very likely to experience process loss. So how can we come to terms with this? I think that the first step is to raise awareness, to measure and visualize how well does we fare right now in our current product development. And the technique I use to that is to try to measure and visualize Brooks' law. So let me walk you through this visualization. What you see on the x-axis, first of all, is the timeline. So this is the progression of the project. The red bars shows something I called the development output normalized per contributing author. So how can we measure a thing like development output? Truth is, we cannot. No one really knows how to do that. So what I tend to do is I use proxies for it because I'm interested in the overall trend. So I might use things like number of completed tasks. If I have the data, one of the best data points is lead time for changes. How long does it take us from the moment we start on a task until we have it in production? Because that ties to actual business value. I mean, there's not a single manager in the world who's going to say, I would like to have a longer time to market, right? So it carries some meaning. Now, the second data point I plot is the black line that you see. That's the number of contributing authors over time. And I pull all of this data out of the version control history. So using version control and this technique, we can basically tell the story of our code base. So the graph you see here, the way I read this is because it seems to be a project that got off to a good start. And then they decided to scale up the organization, and the development output dropped. As a response to that, the deadline became more critical, so let's add more people to it, and the development output drops, and so on. So I would like to claim that what we're experiencing here are some scaling effects, some very likely scaling effects. And this pattern is actually quite common. I like to call it the dreaded crocodile gap, because this is something that's going to eat your project budget. Now, another pattern I've seen a number of times is this. So here we see that it seems like there are less contributors towards the end, and the development output goes up. So what probably happened here is that maybe a team were pulled to a different project, different product, and the development output of each individual increased. So this might be a sign that we have managed to minimize the process loss. I find it fascinating that in some situations you can actually get more done with fewer people. Finally, another very common pattern is this. So here we see we have managed to maintain a stable organization. However, the development output seems to level off and drop off over time. So this is a bit harder to interpret, but it might be due to rampant growing technical debt. Now, what's important to point out is that these visualizations, they cannot tell us what's wrong. They don't answer our questions. What they do is that they help us ask the right questions. And this is the point where it becomes challenging. And the reason it becomes challenging is because on a software project, reality is really just a Rorschach blot. We see what we expect to see. And I would like to read a quote for you. It's one of my favorite quotes. It's written by a psychologist called Bars, who wrote a wonderful book called In the Theater of Consciousness. And Bars claims that humans seem to be driven at least as much by fantasy as by reality. Now, I would like to demonstrate that to you by taking you back to one of my favorite psychology experiments. This is something that was done back in the 1970s. And what the psychologists did here was that they formed two different groups. One group was based in the south of England, and the other group in the north. And then they asked the groups to draw a map over Britain. This is what their two contributions looked like. Can you guess which map that was drawn in the south? That's right. They went to the left, right? So what's fascinating here is that in the south, the participants, they exaggregated the distances in the south, which coincidentally is the area that they are familiar with. The group in the north made the opposite error, of course, and underestimated it. Do you think we have something like this in software too? Oh yeah, we do. So just to try to illustrate the same thing, let's say we have a typical software systems here, and we have a number of teams working on it. Team A works with a particular part of the code, and they might have a very detailed model of how that software looks. They have a good mental representation of it. Team B works with a different part of the code, and they might have a less flattering view of Team A's work. Now, all is fun and games until one day we realize that we want to improve our delivery efficiency. We need to do something to improve. And you ask the teams, and guess what? You're going to get different answers depending on their experience, their exposure to the different parts of the system. So the first challenge here is, how can we create a shared mental model for the whole organization of what the code actually looks like? The technique I use is something I call hotspots. So I'd like to demonstrate the hotspot technique on a well-known code base. This is React.js, developed by Facebook. So it's a well-known front-end library that I think actually a lot of your companies are betting your business on. So maybe it pays off to look a little bit under the hood here. Now, the way you interpret this graph is that you see those large blue circles? Each one of those represents a top-level folder. So this is a hierarchical visualization that follows the structure of your code. It's also interactive, so we can zoom in on it and inspect the details we're interested in. And once we get to a lowest level, we see that each file with source code is visualized as a circle. And you see that the circles, they have different size. That's because size is used to represent code complexity. Now, how do you measure a thing like code complexity? Well, you might have heard about techniques like cyclomatic complexity, Halstead's volumetrics, and so on. And basically, you can choose any one of them that you have easy access to, because what they all have in common is that they're equally bad. Thank you. Turns out that if you start to control for a number of lines of code, those more elaborate metrics don't add any further predictive value. So I tend to use just a number of lines of code. And the reason for that is because complexity, and let me repeat this, complexity is not important on its own. Complexity only matters when we have to deal with it. So what we need to figure out here is, does this potentially complex part of the code, is that something we actually have to interact with as a team? And this is data that you can pull out of your repositories. We can look at things like the change frequency of the code churn. How often do we do a modification to that particular file? And we use color to visualize it. And now, when we combine these two dimensions, we can identify complicated code that we have to work with often. Or to formulate it in the technical depth terminology, I like to view code complexity as the principal, the loan we have taken on. And then I use change frequency as a proxy for interest. Now, we're going to look deeper at hotspots. What I want to point out now that using hotspots, we can start to focus our technical investigations in case we're looking for improvements. And the reason hotspots work well is visible in these three graphs. So please have a look at them. They all show the same kind of data. On the x-axis, you have each file in your system. And those files are sorted according to their change frequency. That is, how often do a developer make a change to any one of those files. And the change frequency is what you see on the y-axis. Now, if you look at the top three examples, you see I have examples from three radically different code bases, implemented in different programming languages, by different teams, by different people, targeting different domains. Everything is different. And yet, they all show exactly the same pattern. They show a power law distribution. And this is something I've found in every single code base I've analyzed so far. And by now, I think I've analyzed around 250, 300 code bases. So I would like to claim that this is the way software evolves. And this is important to us because it gives us a tool to prioritize technical improvements. Because what this means is that most of our code is going to be in the long tail. So that's code that's rarely, if ever, touched. Most of our development activity, on the other hand, is going to be in a relatively small part of the code base. And what the hotspots do for us is that they simply identify the code at the head of the tail so that we can focus improvements to where we are likely to get a real return on that investment. Now, let's say we come across a hotspot and we look at it and we realize we need to improve it. How do we go about that? How can we refactor existing code? I do have an answer for you, but first I need to take you on a brief detour. And actually, I'm going to do something I almost never do. I'm going to share something personal. I figured out that a Keynote, that must be the right opportunity for that, right? So this is something that happened 10 years ago. At that time, I broke up from a long relationship. So there I was, introverted software developer in my mid-30s. How do I go about finding a new partner? I mean, I couldn't even remember the last time I went to a date. So I sat down and thought about it for a while, and then I decided to do the only sensible thing a programmer in my situation could do. I decided to hack the system. Because I happen to know that there's a whole subfield of psychology called the psychology of attractiveness. So I started to study up on it. I bought the textbooks, but I pretty soon got sidetracked by this thing called beauty. Because beauty, when I start to read about the psychology of attractiveness, I kind of thought that beauty is a subjective thing. But it turns out beauty actually has an objective core that's shared all across the world, across different cultures. And what's also fascinating with beauty is that it has a profound impact on us. It impacts how we perceive other people. So just to give you an example, did you know that beautiful people are considered to be not only more friendly and social, but also more competent and intelligent based on looks alone? This isn't fair, but it's great news for us, right? So when I realized that, what I started to do was I started to basically look for a quick fix. And I found one. And it's too good not to share with you. Not that you need it. But anyway, do you want to know how you can become more attractive with a minimum of effort? All you need to do is eat a lot of fruit. And this is actually some hard science behind this, that an excess consumption of fruit is going to make you be perceived as more attractive. And I'm going to explain why that's the case in just a minute. The reason I tell you all this is because I have since come to use beauty as a guiding principle when I write code. But I want to point out that when I talk about code and I talk about beauty in code, what I'm referring to is beauty as a mathematical concept. That's what I'm fascinated about. So what is that? How do we define beauty? Well, let's have a look. Have a look at this couple. These two won a beauty contest. And that's not that interesting. What might be interesting is that none of them actually exist. These people were created in a psychology lab. They were part of an experiment. And what the psychologists did here was that they took photos of individuals and morphed them together using computer software. And it turns out the more photos they morph together, the more attractive the end result. And this is a little bit surprising, because if you consider what actually happens when you morph photos of individuals, what happens is that you erase individual differences. And what that basically means is that beauty is nothing but average. And what's even more fascinating is that beauty is not so much defined by what's there. Beauty is the absence of something. It's the absence of ugliness. And that in turn turns beauty into a negative concept. So, why is beauty so important to us? Well, the leading theory in attractiveness psychology is something called the good genes theory. Now, if we think about life, and I mean life in the larger evolutionary perspective, In the larger evolutionary perspective, our main task as humans is to reproduce. Now, think back to the Stone Age and say that you want to meet a partner. What's important from an evolutionary perspective is that your partner has healthy genes. And back in the Stone Age, it wasn't exactly easy to come across a DNA test. These days, it's doable, might not be socially acceptable. So the leading theory here is that we have come to use beauty as a proxy for health, a proxy for good genes, with the idea that if you could grow up and have a face with mathematically average features, you were most likely shielded from infectious diseases. So when I heard about this, I started to think, could we develop one such thing as a good genes theory for code? And what would healthy code look like? The way I approached this was by starting to read up on a lot of research on defects, maintainability, and code readability. And I tried to figure out what those constructs are. And fascinating enough, they turn out to be both technical and social in their nature. And I would like to share both with you here. So let's return to React.js and the hotspot we uncovered a while earlier. Now, this is a small piece of that hotspot in React. React Fiber begin work. Now, if we look at this and apply our beauty principle, what immediately stands out to me is this: some deeply nested logic. Now, this is also something known as the arrow pattern, right? And I would like to point out to you why this is a problem, always. And the way I want to do it is by having you do an IQ test. You weren't prepared for that at all, right? You thought you were going to sit there and relax. But you see, this is what happens when you put a psychologist on stage. So if you have ever tried an IQ test, modern IQ tests tend to be based on something called Raven's progressive matrices. And they look pretty much like this. So the way it works is that you have a number of rows and columns, and one image is missing. And your task is to find the missing image from the two bottom rows. Does anyone know the answer? Yeah, 8. Excellent, of course. Let's raise the bar. What about this one? Which piece is missing? This was harder, wasn't it? I know the answer. I have it on screen here. It's this one. So the way you approach this, the previous was pretty simple, right? You have two images, you combine them, and you get the third image. This one is more tricky because what you do here is you also combine the two images, but then you have to subtract the overlapping lines. So this is harder, and the reason this one was significantly harder has to do with a construct called working memory. Working memory is like the mental workbench of your brain. So it's working memory you use to perceive, integrate, manipulate, and reason about information in your head. So it's working memory you use when you do a Sudoku, solve a crosswords, or try to read code. So working memory is really, really important to us as developers. You might even need it as a manager. What do I know? But the bad news are that working memory is also a strictly limited cognitive resource. Has anyone heard the number 7 plus minus 2? The number of things you can keep in your head, right? That was defined by Miller in 1958, and modern cognitive research is much more pessimistic about our capabilities. It might be as few as 3 to 4 things that we can keep in our head at once. So let's return to that IQ test that you just did and passed with flying colors. Let's return to this and see why those things were hard. In the first case, you had to keep 2 things in your head. In the second test, you have to keep at least 3 things in your head. So if you translate thing into programming, what does it mean? It means state. So if we return to the code we uncovered in React.js, and let's pretend that we have some maintenance tasks to do. We need to go into that code and fix a bug. If we need to do that bug fix, we need to do that bug fix while keeping 1, 2, 3, 4 things in our head. And that basically means with deeply nested logic like that, we are operating at the edge of our cognitive capabilities. It's not a wonder that things go wrong. And there's some very good research that shows that roughly 20% of all coding mistakes are due to things like deeply nested logic. So please, don't turn your code into an IQ test. So what can we do instead? Well, we can learn from this book. This is one of the best biographies I ever read. This is a biography of Bobby Fischer, who was at one time the best chess player in the world. And what's fascinating is that the author is a chess player too. And the author tells the story of how he attended a chess tournament. Bobby Fischer attended the same tournament, and Bobby had already won his game. So Bobby was on his way out. So he was walking out, and he walked by the author, and he kind of just glanced at his chessboard, and then he moved on. A couple of months later, they two meet again. And the first thing Bobby Fischer asks is, "Hey, did you play queen to d4? And the author was like, "Wow, what are you referring to?" It turned out Bobby had memorized the setup on that chessboard months earlier. And not only that, he had figured out the best next move. That's pretty impressive, isn't it? Let me tell you, psychologists, they love chess players because they're an excellent way to study working memory. And the way you do this is typically you put up a chessboard and then you ask people, how many positions can you remember? And if you do this with expert chess players and novices, it turns out that the experts outperforms the novices with a wide margin. But now, do this twist on the experiment. Repeat it once again, but now you rearrange the pieces on the chessboard. You put them in a random order, an order that can never occur naturally during a game. Maybe put both bishops on the same color. The moment you do that, the situation looks quite different. So the chess players, the expert players, they lose their advantage. And that kind of indicates that a chess player, their working memory is not necessarily better. It just works differently. It works differently because what chess players, what expert players remember are not individual pieces. They remember patterns, groups of pieces. And this is a technique known as chunking. You take some low-level information and group it into a higher-level abstraction. You can still only keep 3 to 4 things in your head, but now each thing is going to carry more information. And this is a technique I use all the time when trying to work with legacy code. So let's return once again to the React hotspot. When I come across code like this, the first thing I try to do is to identify the different responsibilities of it. And then I take those responsibilities, I extract them into a new method, and I put a name on it. And the moment I put a name on it, I have created a chunk. And using this rather simple technique, we can go from this to that in just a minute. And I would like to claim that the code on the right is somewhat easier to reason about. So now we can fit more of the code into our head. And this in turn tends to reveal the overall algorithm. And that in turn makes it easier for us to identify the next possible refactoring step that can make a real difference. So yeah, I couldn't help to see that when I did this refactoring, I noticed that, hey, this looks like it could be the start of a refactoring towards the design pattern command, which would reduce the complexity even more. So chunking is one of the simplest and also the most valuable techniques we can use for our code. Of course, we could take it to the extreme. So one thing I tend to do is I tend to take a couple of days off, sometimes a whole week each year. And I tend to dedicate those days to learning something new. So 2 years ago, for example, I took a week off to learn array languages properly. So odd languages like APL and J, which was pretty fun and interesting. Last year, I took some days off to code machine language on a Commodore 64. So it's not so much about finding something that will be immediately useful in my day job. It's more about taking a step back from all of that and try to remind myself why programming is fun. So this year, I decided to do something different. I decided to implement a deep learning network from scratch using functional programming. And to make it a challenge, I decided to introduce some constraints. I decided that I wasn't allowed to use any conditional logic at all. No if statements, no for loops, no switch case, which basically meant I had to treat the whole program as a sequence manipulation. And it turned out it was a pretty interesting experiment. It was doable, and I had been writing some tests as I went along. But the big surprise came afterwards. And this might be obvious to you, because in a way it is, but I got surprised because the effect was so strong. It turned out that with a single top-level test case, I could get full code coverage. And the reason I can get that full coverage is because there are just a single logical path through the program. So this is not, I repeat this is not a technique I recommend that you apply in your day jobs, but I do think it's really valuable as a learning vehicle. I learned a lot by doing this, so it's something I recommend that you play around with. With that covered, let's move on to the social side of code and see how our mental models can be affected by the way we organize. And for these case studies, I want to look at something different. I would like to look at the Roslyn codebase. I'm a big fan of Roslyn. Roslyn is Microsoft's compiler platform. And what's fascinating about it is that it implements two compilers itself. So if we zoom in a little bit, we see the C# compiler to the right and the Visual Basic compiler to the left. We also see already here, this is 5 million lines of code, but we do see something that looks like a pretty significant hotspot in the C# compiler. What's that? Well, let's zoom in a little bit. It turns out that it's a test suite of C#'s nullable reference types. And when I picked up the code, I noticed that that test suite consists of 93,000 lines of code. Is that a lot? I don't know. I wasn't sure, right? So I'm always trying to put things into context. So to provide you with some context, the complete software for Apollo 11's guidance computer is 150,000 lines of code. And that one was written in assembly. The other one is a high-level language. So it seems to be that C# nullable reference types is an equally hard problem to landing on the moon. The good thing might be that, the next time someone tells you, hey, why is this taking so long? It's not astrophysics. You can point to this slide, right? Now, why am I focusing so much on size here? First of all, from a practical perspective, that hotspot, when I tried to view it on GitHub, it crashed my Chrome tabs. It simply ran out of memory. So we have a practical issue. But what I consider more serious is when we add a social dimension of code. So let's look at that. To your left, you have the normal hotspot map of Roslyn that I showed you earlier. The map to the right shows a different landscape. The map to the right shows an overlap in contributors. So the more parallel development you have by different people, the more red the corresponding part of the code. And what I tend to find over and over again in the code bases I analyze is that hotspots tend to become coordination magnets. And there's a reason for that. The more responsibilities we stuff into a module, the more reasons it has to change. And factors like parallel development in the same parts of the code are important because organizational factors are some of the best predictors of defects. It turns out that the structure of the development organization, it's a better predictor of software defects than any code properties. What's even more fascinating is that this is true even in the presence of a strong peer review culture. So, like I said, the reason I show Roslyn here is because I'm a big fan of the project. It's a high-quality product. Another high-quality product is the Linux kernel, which is known for its peer review process. And the last study refers to a study on the Linux kernel, where it turns out that organizational factors like parallel development, not only do they predict defects, they also tend to predict more severe defects, things like security issues. So why does this happen? Well, I do have an idea. It's because social factors will influence how we perceive a code base. So when we developers reason about a piece of code, we never remember the code exactly like it looks. We have an imperfect mental model in our head that we try to reason about. And the challenge is, of course, that let's say that you implement a piece of code yourself today. 3 days later, that code will look completely different because 5 other contributors have been writing in that code in the meantime. So the next time you go into the code to make a change, you're going to do that code based on an outdated mental model. And when we fail to control these social factors, we might run into these scaling effects. And this all ties back to Brooks' law, where excess parallel work in the same parts of the code, it's a type of process loss that might make it very expensive when trying to scale an organization. I have seen organizations deal with it, and the thing I have seen that seems to work best is to take a step back and start to modularize large hotspots. Modularity is really important, not only on the file level, but also on the architecture level, of course. But it's not just any modularity. What I have seen works best is when the modularity, our modular boundaries, are based on concepts from the problem domain rather than the solution domain. Because if we manage to pull that off, that's the level we tend to parallelize our work on, where we tend to parallelize tasks. And if we have concepts from the problem domain, we also create natural boundaries for different developers and different teams. And I think that this is something that's going to become even more important in the years to come. And the reason I say that is because of this: microservices. So when I started to work with code analysis 4 years ago, most organizations I worked with, they talked about microservices, but very few were operating them. Today, it's the reverse situation. Virtually every company has some kind of microservice project. And this is important because what it means to us is that tomorrow's legacy code is going to be microservices. So let's stay a step ahead here and see how we can raise awareness and analyze microservice architectures. What I find fascinating is that in a microservice architecture, the most important aspects are not necessarily properties of the code, but properties of the whole system. What do I mean by that? Well, I mean that in a microservice architecture, things like implicit coupling, implicit dependencies between services, or team coupling are much more important than the particular constructs in the code. So, what does a microservice architecture look like? Well, for this case study, I'm turning to something different. This is Spinnaker, a microservice system, a continuous delivery platform developed by Netflix and Google. And Spinnaker consists of roughly 35 different Git repositories, each one of them encapsulating a specific microservice. And the first thing I like to point out is that what I find so fascinating with hotspots, hotspots are built from version control data. And version control data is language neutral. So we can get this holistic model no matter how many different programming languages we use. And we could, of course, use this hotspot analysis to start to identify potentially complex code. We can start to improve it. But I have found in microservices, the service level tends to be more important. So what I usually do is I aggregate contributions to individual services. And this might help us detect services that grow too complex. So it could be an indication that we have too many responsibilities stuffed into a service. But we need to do better. We need to figure out what happens between the services. And this is how I typically approach it. This is a dependency graph over the services in Spinnaker. And I'm going to return to this one in 30 seconds. I just want to show you how I calculate this. Since this is microservices in different Git repositories, there's no direct dependency between them in the code. So what I use is that I turn to process data and version control data. I simply look at which services tend to be changed as part of the same feature set over and over again. And this is what I visualize. This is a concept known as change coupling. And using change coupling, we can identify things like a cluster of services that seem to evolve together. In this case, I would like to focus on the red line. So the red line, the red color, indicates that this is a dependency that increases in strength, grows stronger and stronger. And the reason I would like to look at that is because that dependency, what happens when we consider the organizational side? What would it mean if these services are developed by different teams? What would the process loss be? How much additional coordination needs do we take on? And this pattern is the reason for one of the most common questions I've gotten over the past years. And that question is, should we use component teams or feature teams? We kind of tried both and none of them really seems to work. The reason that happens is because in a tightly coupled architecture, if you put component teams on it or domain teams, what tends to happen is that you get very, very long lead times. So you switch to feature teams and suddenly your whole application turns into a gigantic coordination bottleneck. So how can we resolve this? I think that the only real answer is in one of my favorite movies. The only winning move is not to play. Because I simply don't think we can fix what is fundamentally an architectural issue by purely organizational changes. You know, it's a little bit like trying to play football with a cement lump. It's going to be a slow game. It won't be quicker just because we switch to basketball. It's the raw material that needs to be refactored. And the way to rethink it is very well described in a brand new book called The Unicorn Project, came out just the other day. And I would like to read my favorite quote from that book. And that quote is that simplicity is important because it enables locality. And locality in our code is what keeps systems loosely coupled, enabling us to deliver features faster. So this whole idea of locality is fundamental to the business as well. Locality on all levels is what helps us meet not only time to market, but also to respond rapidly to new requirements and minimize the process loss between different teams. And the first step towards those improvements is to start to measure and understand how well does our current architecture supports the way our system evolves, using visualizations, using data. So psychotherapy is all about reflection and introspection. And in this session, we have taken our own products and artifacts, code and process metrics, and turned a microscope of statistics onto ourselves. And by doing that, we can get insights into this complex human endeavor that we call software development, and start to make better decisions with less bias, guided by data. And if you're interested in diving deeper into this, I have my new book called Software Design X-Rays, where I cover all of this stuff with some hands-on exercises and tooling examples. If you want to explore some well-known open source projects, then I recommend that you check out Codes.io that I work on right now, where I have a number of interactive analyses. And finally, I blog at mpr.com and adamtornhill.com. I'm going to hang around afterwards in case you want to ask me anything. For now, I really just want to take this opportunity and say thanks a lot to all of you for attending my session, and may the code be with you. Thank you.
Totally amazing. Totally amazing. Thank you all for a wonderful first day. Have a really good time at quiz night tonight. Don't forget your train tickets.